There's this real obsession right now in AI with what everyone calls the black box. We pump all this data into these huge neural networks. They give us an answer, and if you ask, hey, why'd you pick that?
The model just kind of shrugs.
Exactly.
Yeah.
It's a total mystery.
It is. It's the whole trust me, I'm an algorithm problem. And look, for generating some cool art, that's one thing. But for big decisions in finance or medicine, that black box is, well, it's a little scary.
Right. And that is exactly why I was so fascinated by the research we're looking at today. We're actually taking a step back from the LLM hype for a minute.
A welcome break.
And we're going back to one of the true workhorses of machine learning. It's understandable, it's reliable. We're talking about the random forest.
The random forest is really the anti-black box. It actually shows its work.
Okay.
If a random forest rejects your loan, you can literally trace back through the decision process and see why.
But here's the catch, and this is the core of our deep dive. We all know how a random forest runs on a single laptop. But what happens when you try to scale it up? Like supercomputer level scale.
Yeah.
We've got a paper here from researchers at the Karlsruhe Institute of Technology, or KIT. It's called Scaling Laws of Distributed Random Forests. And it turns out it's not as simple as just plugging in more machines.
No, not at all. It's a minefield of trade-offs, really. The KIT researchers basically stretched this algorithm across a massive computing cluster. We're talking nearly 5,000 cores, just to see where it bends and where it breaks.
And they found some things that are honestly pretty counterintuitive, especially around data privacy. But before we get to the breaking point, let's just ground ourselves. What exactly is a random forest?
So imagine you have a really tough decision to make. You could just ask one expert, right? That expert is your decision tree.
Okay, a single logical path. If this, then that.
Exactly. If it's cold, wear a coat. Simple. But, any one expert can be wrong or biased.
Or just having a bad day.
Right. So a random forest says, don't trust one expert. Instead, you build a council, a whole room full of them. Hundreds, even thousands.
A democracy for data.
It is. But here's the key word, random. If all your experts had the exact same training and saw the exact same data, they'd all make the same mistakes.
You just have a very confident but very wrong council.
Precisely. So the algorithm forces diversity. It gives each tree a slightly different random slice of the data that's called bootstrapping. And at every decision point, it only lets the tree see a random subset of the features.
So you're intentionally putting blinders on the individual trees to make the group as a whole smarter.
That's it exactly. It's called ensemble learning. All the individual errors just kind of cancel each other out.
Which sounds perfect. And because each tree is independent, you'd assume this is the ideal algorithm for a supercomputer.
You would. In computer science, we call that embarrassingly parallel.
Meaning you'd have to be embarrassed if you messed it up.
Yeah, it's supposed to be that easy. But the KISS researchers found, well, it's not quite that simple. Let's talk about their setup.
This wasn't just a few servers in the cloud.
Oh, no. They were serious. They built a hybrid parallel system on a high-performance cluster. They used up to 64 compute nodes.
And a node is basically its own powerful computer, right?
Exactly. Think of it like an office building. And inside each of those 64 buildings, you have the workers, the cores. All told, they had 4,864 cores at their disposal.
That's a ton of processing power.
It is. And to get them all talking, they used a two-tiered system. They used something called MPI to let the different buildings talk to each other.
Long-distance calls.
Right. And then inside each building, they used shared memory. So the workers, the cores, could just shout across the room. It's much faster.
Okay, so they've got this beast of a machine. And they fed it some serious data, too. Not just toy problems.
No, they used synthetic data where they could control the variables, but also the HIGGS dataset.
From particle physics.
Yep. It's a classic hard problem, finding a tiny signal in a whole lot of noise.
Okay, so the stage is set. Let's get to the core of the paper. The scaling laws. They talk about strong scaling versus weak scaling. I feel like these terms get thrown around, but they mean very different things.
Fundamentally different things, yeah. And it's a classic mistake to mix them up. Strong scaling is all about speed.
Okay.
You have a fixed problem, let's say a pile of 10 million records. The question is, if I double my computers, does it finish in half the time?
If one painter takes an hour to paint my wall, 2 painters should take 30 minutes.
That's the ideal. Yeah, that's linear speed up. Then you have weak scaling. That's about capacity.
Right.
With weak scaling, you say, okay, I'm doubling my painters, but I'm also going to give them a wall that's twice as big.
So the goal isn't to be faster, It's to get more done in the same amount of time.
Exactly. You want to maintain efficiency as the scale of the problem grows.
So let's start with strong scaling. Did the random forest get faster when they added more nodes?
It did, but it's a huge but here. Initially, the speedup was great. On 64 nodes, they got a speedup of almost 32 times.
Wait a second. 32 times faster sounds okay, but if I'm paying for 64 nodes, shouldn't it be closer to 64 times faster? I feel like I'm losing half my money there.
You've hit the nail on the head. They hit a saturation point, a ceiling.
What do you mean? How do you run out of work with 10 million data points?
Well, think about it. You have a forest of, say, 500 trees. If you have 64 nodes, you start dividing up the work. Pretty soon, each node is only responsible for like 7 or 8 trees.
I see where this is going.
The administrative overhead, just the time it takes to set up the communication and coordinate everything, starts to take longer than the actual work of training those 7 little trees.
So you've got 64 painters, but you only gave them a garden shed to paint. They spend more time bumping into each other than actually painting.
That is the perfect analogy. So strong scaling has a limit. You can't just throw hardware at a fixed problem forever.
Okay, so that's the limit on speed. What about weak scaling? Making the forest bigger as you add more computers.
Now this is where random forests just sing. The efficiency stayed above 0.96.
0.96. That's almost perfect.
It's incredible. It means if you double the resources and double the problem size, it takes almost exactly the same amount of time. It never saturated because every node always had plenty of work to do.
And a bigger forest is a smarter forest, I'm guessing.
Yes, and this is a key takeaway. In that weak scaling test, the accuracy of the final model went up significantly. Because with 64 nodes, you're not just doing the same job faster, you're doing a fundamentally better job in the same amount of time.
So the lesson is, if you have access to a supercomputer, don't just use it to save an hour on a small model. Use it to build a much bigger, smarter one.
That's it. Random forests absolutely love volume.
All right, so we've trained our massive, super smart model. Now we have to actually use it, the inference phase. And I was really surprised to read that this is where things can get really complicated.
It's a huge logistical problem. The researchers looked at 2 main strategies. Strategy A is the global model.
And that's basically everybody gets a copy of everything.
Yep. After your node trains its little patch of trees, it broadcasts them to every other node. And every other node sends their trees to you.
So, if my node trained 100 trees, and there are 64 nodes, I end up with 6,400 trees stored on my machine.
Yes. The entire global forest sitting in your local RAM.
That sounds heavy.
Incredibly heavy. On one of their data sets, they found that just the gathering phase, just moving the model around, took 5 times longer than the actual training itself.
That's insane. You spend 10 minutes studying for the test and 50 minutes at the photocopier.
And the memory cost, it's brutal. We're talking up to 160 gigabytes of RAM on a single node.
So why on earth would anyone do that? It sounds terrible.
One big reason, privacy, or maybe isolation. If you have the whole model locally, you can run a prediction without talking to anyone else. You don't have to send your sensitive test data across the network.
Okay, that makes sense. A hospital wants to use the model on its own patient data, right there. But what's the alternative if I don't have 160 gigs of RAM to spare?
The alternative is strategy B, global voting.
Okay.
Here, the trees stay where they were trained. When a new test sample comes in, we just send the sample to everyone. Each node runs it through its local trees, and they just shout back their vote.
I vote yes. I vote no. And someone just tallies it up.
Exactly. It's super lightweight on memory, much faster to set up.
But the network has to be up and running.
The network has to be perfect. If your connection drops, you've just lost access to 98% of your model's brain.
So there's another scaling law. It's a choice. You either pay in memory with the global model, or you pay in connectivity with global voting.
That's the trade-off. There is no free lunch. You're buying RAM or you're buying bandwidth.
Now, I want to get to the part of this paper that I think has the biggest real-world implications. So far, we've talked about distributing the model. What about distributing the data?
Right. In a lab, all your data is in one place, but in the real world, you have things like federated learning. Hospital A has its data, Hospital B has its data, and they are not allowed to merge it.
So the researchers simulated this. They split their training data into 64 tiny pieces, one for each node. And what happened?
Well, first, the speed went through the roof. They actually saw what's called superlinear speedup.
Superlinear. That sounds like marketing speak. How can you be faster than the math says you should be?
It's all about something called CPU cache. When you slice the data that small into a 164th chunk, That tiny piece fits perfectly into the processor's ultra-fast memory, the cache.
Oh, I get it. It's like having your tools right in your tool belt versus having to walk back to the truck every time.
That's a great way to put it. The processing was basically instant. It was incredibly fast.
I'm sensing a very big but is coming.
A massive but. The accuracy completely tanked.
Why?
Data starvation. A model can't learn patterns it never sees. When they split the data 64 ways, the trees on each node were only seeing about 1.17 samples for every feature.
1.17 samples. That's not a pattern, that's an anecdote.
Exactly. It's like trying to learn English by reading a single page from a phone book. The local trees were just too weak because they were starved of information.
So it sounds like that's a dead end. If you split the data, you kill the model's quality.
You'd think so. Normally you'd be right. But this is where the paper delivers its big plot twist.
Okay, I'm ready.
Everything we've discussed so far assumes the data is IID.
Independent and identically distributed. The nice, clean, well-mixed data from a textbook.
Exactly. Every node gets a representative slice. But real-world data is non-IID. It's messy. Hospital A specializes in cardiology. Hospital B is a pediatric clinic. Their data looks totally different. That's called partition imbalance.
So the researchers decided to deliberately make things messy. They took a data set that was already globally imbalanced, meaning some outcomes were very rare, and then they made the local data imbalanced too.
They did. They'd give Node 1 mostly examples of Class A and Node 2 mostly examples of Class B. Intuitively, this should be a complete disaster.
It should be a train wreck. You have a hard problem, and you're feeding your workers biased information.
But it wasn't. In fact, they found that when the global problem is hard and imbalanced, having that local, messy, imbalanced data actually improved the global accuracy.
Wait, what? Making the data more biased made the final answer better. How?
It goes back to our council analogy. If every expert sees the same balanced data, they all mostly see the majority cases, so they all learn to ignore the rare stuff.
The whole council shares the same blind spot.
Exactly. But if you skew the local data, suddenly Node 5, just by random chance, gets a huge chunk of that rare case. Node 5 becomes a specialist.
Ah, so Node 5s are the one person in the room who's seen this weird thing 100 times while everyone else has only seen it once.
Precisely. And by forcing the nodes to be different, you dramatically increase the diversity of the whole ensemble. When you add up all the votes, the council is smarter because you have these specialists who cover the blind spots.
That is such a fascinating insight. It's like the business case for having a diverse team, but proven with math in a machine learning model.
It really is. It challenges this core assumption that we always have to clean and homogenize data. This suggests that, for random forests anyway, that messiness is actually a feature, not a bug.
So let's try to wrap this up. If I'm a data scientist listening to this, planning a distributed project, what's my takeaway? What's the cheat sheet?
I'd say 3 big things. First, know your scaling goal. If you have a fixed problem, don't just keep adding computers, you'll hit a wall. But if you can grow the problem, that's weak scaling, and random forests are a fantastic investment.
Okay, go big. What's number 2?
Second, decide on your inference strategy upfront. If you need absolute privacy and can't share test data, you need to budget for a lot of RAM for that global model. If your network is solid, global voting is way more efficient.
And the third?
Don't fear the mess. If you're doing something like federated learning, don't worry so much about making every location's data look perfectly balanced. That imbalance might be the very thing that helps your model spot the rare critical events.
It's a really cool look at the nuts and bolts. We talk about AI like it's magic, but when you get down to the metal, it's all about these engineering trade-offs. Speed versus accuracy, memory versus bandwidth.
Absolutely. And this paper provides a fantastic, rigorous roadmap for how to think about those choices.
I will leave our listeners with one final thought. We often think about privacy constraints, like data being stuffed inside a hospital, as a problem to be solved, an obstacle.
Right. We think, if only we could pool it all together, the AI would be so much better.
But based on what we just learned about these specialist nodes and the power of diversity, maybe that's the wrong way to look at it. What if those walls between our data are actually a good thing? What if the fact that we can't merge the data is forcing our algorithms to become a more robust, more diverse council?
That's a great thought. It reframes the privacy problem as a performance opportunity.
Something to think about. Thanks so much for walking us through this.
My pleasure. Thanks for having me.
We'll catch you on the next deep dive.